Hi, Marcos,
Hello, Ellie. Hello, everybody.
and good afternoon for everybody, and good morning for people in the US and Canada. Um, how are you, Marcos? Are you been working on special project these days or this last months?
Yes. I am working in different projects with a lot of hot, but because here in Spain, temperature is like crazy. But yeah, I working in last week, for example, in an inductor for an automotive sector. Okay, an inductor with a U core, a splitted winding. So yeah, very interesting. Okay, because you need to, you know, there are a lot of requirements in the sector, so you need to fulfill everything.
Wow, so interesting. And I had a question about the topic today because we are going to talk about the flybacks.
Mm.
So why flyback? Because it's the most common topology normally electrical engineers use in the projects. Or uh, why do you think it's important to take into account?
Well, I don't know if this is the most common, but probably is one of the most common, okay, because it's a very simple converter design with isolation and it's used in many applications. In fact, all the charges that we have from our laptops, from mobile phones, has a flyback converter, or most of them, because it's cheaper and it's easier to design. Okay, it's not the most efficiency converter, but for this, if you want something with high efficiency, with more power, there are another topologies better.
Okay, good. So I'm going to start sharing first um, our weekly slide about our products because I think it's good to distinguish that we have two tools. A lot of people know Frenetic Simulator, which is the tool appropriate for design and simulate your custom magnetics, and we can get up to 85% of accuracy, and that's important because you have mentioned that maybe flyback is not the best option always, but it's the cheaper and has another different advantages. And I think that's why maybe it's important to count on other tools like Frenetic Simulator uh, to improve the design. The other tool we are going to see today is also Frenetic AI. Frenetic AI, it's for doing calculation of the power converter. And this is important because we are going to see how these two tools connect one with other, and how easy is to create a project from Frenetic AI and open directly in Frenetic Magnetic Simulator and then playing with the specs. So, Marcus, I'm going to stop sharing, and you can you can start the demo for today.
Okay, thank you, Eileen. Well, okay. Hello, everyone again, and thanks for attending or for joining today webinar. Today, I'm very excited about the topic that we are talking about because converters and also flyback transformer design, it's a very particular design because most of you know probably it's physically a transformer, but it's working more as an inductor, storing energy in the primary side, secondary side. But today I want to focus more into common mistakes that also senior engineers commit, okay, when designing flyback transformer, okay. In fact, most of these mistakes, it's something that it happens to me in the past, okay. And I would like to share with you all my knowledge and the way to mitigate or to take into account these mistakes. So let's start with the first one, which is related to the auxiliary winding. So here we have a simplified schematic of the flyback converter, okay? But here there are missing things. The first one is the IC controller that you have here that drives the MOSFET in the primary side with a PWM signal. And this PWM signal has a duty cycle that needs to be adjusted in a way. And the way to do that is with a feedback pin, okay? With it could be done in two ways. The first one, most of you probably see in some reference design, which is having a voltage divider in the secondary side. Then you have here a voltage that has, okay, there is another circuit here, voltage reference, and so on. And there is a last component here, which is an optocoupler, which basically is to keep the isolation between the primary and the secondary side, okay? And this way probably is the best way to do the feedback loop, okay? But there are another way, okay, to do that, which is using an auxiliary winding, okay? In fact, it's cheaper than this because you don't need the optocoupler and you don't need the circuit in the secondary side, okay? So you have another winding here with his own rectification, okay? And this output, you can feed directly the feedback pin, okay? You can also use the voltage divider, okay, if you want, because sometimes this auxiliary winding is also, it's already used for biasing the IC, okay, to feed the supply of the IC, okay? But here, the main thing that we need to take care or be careful is the position of this auxiliary winding in the transformer design, in the transformer coil former, okay? So let's go to Frenetic simulator, okay? And here, what I have is a real example, a real case of a customer, okay? It's a flyback 2.7 watts with two secondary windings and one auxiliary winding in the primary side, okay? So the customer here did the design with the suggestions and he get EFD 15 with this core material and the following configuration in the winding, okay? So you have the primary, the secondary one, secondary two, and the auxiliary winding. So then my customers see that electrically the design seems okay because you have maximum temperature, 73 degrees, you have total losses 0.14, small losses, so it seems fine. But if we take a look to the leakage inductance that our tool calculates based on the model, we see that the leakage inductance is very high in the auxiliary winding, and in the secondary side is also high, okay? So, well, even if the transformer is okay for the electrical perspective, for the working perspective, if we place this transformer in our circuit, we will have a lot of problems with the leakage inductance. We will see in the second common mistake, which is more related with parasitic effects of the transformer. But if we focus in on the auxiliary winding, well, the idea of the auxiliary winding in this case is to do the control of the system. So the higher the leakage in the auxiliary winding, the lower the accuracy in the control, okay? And also, if we have the auxiliary winding close to the secondary side, we can produce some bad effects in the secondary side that we don't want, okay? So the idea or the recommendation always for the auxiliary winding, if you have in the primary side, is to place as close as possible to the primary winding. You can do it that, okay? Here in the customize option, placing, for example, the auxiliary winding in the middle of the primary. You can apply the chains, and if you run the simulation, what we will see is that the leakage inductance referring to the primary side from the auxiliary winding, it's smaller than previously. And that could be fine, okay, regarding the regulation. The problem is that even if we have here a small leakage, which in this case is 26, we have high leakage in the two secondaries. So, okay, we have a good regulation, but we had very bad effects in the producing by the leakage. Okay, so we at the end we need to think about a trade-off, okay, between having a good coupling with the auxiliary winding, but also having interleaving with the secondary side, okay. So in this case, what you will see in most of the transformer design for different manufacturers are the secondary side in a sandwich approach, okay. So you have the primary in the first layer and in the last layer, the secondary side in the middle, and the auxiliary winding you have it close to the primary side. It's not the best position for the auxiliary winding, okay, because you are close to the secondary one, but it is better than having without any interleaving and have it in the other layer, okay. So at the end, what we will get is a, let's say, balanced transformer design with all the leakages, okay, very close to each other, okay. As you can see, we have 67, 74, and 85, okay. So in the overall performance of the system, it could be better, okay. So my conclusion here is be careful about the position of the auxiliary winding. If you have the auxiliary winding in the primary side, you need to place the auxiliary winding as close as possible to the primary winding. In the opposite way, if you have the auxiliary winding in the secondary side for any reason, you need to place as far as possible to the primary side and as close as possible to the secondary side to improve the coupling. Okay, so come back to the presentation. The second common mistake, okay, we talked a bit about in the auxiliary winding, we talked about the leakage inductance and how bad it is for flyback designs. But here we need to account that it's not only the leakage inductance, the problem that we can have in a flyback converter, okay? So this represents an ideal flyback converter that it's not possible to get in real hardware. Because at the end, we don't have an ideal switch. We have a MOSFET with capacitance here. And also we have the capacitance in the input side that for this seminar, webinar, sorry, we don't want to model it for the moment. And then we have here also a capacitor in the rectifier diode. And in the transformer, we have, first of all, the leakage inductance. You can represent here, referring to the primary side. You have also a series resistance, which is the resistance of the copper in the primary side and in the secondary side. But you have also capacitors. You have one in the primary side and another in the secondary side, which are in the intra-winding capacitance. And you have another one between the primary and the secondary, which is the interwinding capacitance. And there is some missing thing here. Okay, a part of the magnetizing inductance that you can put it here as an external part. But there is another missing part that it's very easy to forget about that, which is a parallel resistor, which represent the core in the transformer. Okay, because this parallel resistor, we will see later, it plays a critical role here in the behavior of the whole parasitics for the circuit. Okay, so if we go to LT-SPICE, okay, here we have the ideal model. So if we run the simulation and we take a look to the output side, we have 24.4 volts from an input voltage of 100. This LT-SPICE file was created with Frenetic AI. And if we take a look to the switching node, it's perfect. It's very clean. Okay, so if we start to add parasitics, the first thing that we can add is the series inductance, the series resistance, and the leakage inductance, but we don't know the value because we don't have any designs. So we can help with Frenetic AI, and well, apart of generate the LT-SPICE file, we can suggest a magnetic design, and with this magnetic design, we can open it in Frenetic simulator, and in the datasheet part, even if this is not the final design, we can check the DC resistance, and the leakage inductance. So we can put it in our circuit, okay? So we can put here 200 millis, 19 millis, and here for the inductance, there are two ways to do. One is the ones that I did right now, which is putting the coupling factor, and then assuming that the coupling is not perfect, which is in the reality that's what happened, or you can put a perfect coupling and represent the leakage inductance as an external inductor referring to the primary side. So both cases are okay and are fine. Okay. The only thing that you need to take care here is that this is like a percentage of how much are coupled the primary and the secondary. So regarding the leakage inductance that you have in your design, you need to put the correct number here to see the coupling, okay? And as we can see, the simulation, first of all, it's slower than previously because there is a new effect, which is this one, okay? Let's see first of all, the output voltage, which in this case is 0.4 volts less. So we need to take into account that there is a voltage drop produced by the leakage inductance and the series resistance. And if we take a look to the switching node, we see this huge voltage spike, which is 45 kV, which, okay, I can say to you that this is not real, okay? So it never happens. You cannot put your transformer in the hardware and you never see this. First of all, because probably you cannot measure it in the oscilloscope, but there are some missing parasitics that also affect to this voltage spike, okay? So we don't model the output capacitor of the MOSFET. So if we take the output capacitor, in this case I put a common number, okay, which is 100 picofarads. It is true that this capacitor, it varies depending of the BDS, so probably the best way to do that is modeling the MOSFET with a BD MOST model, or maybe with the model from the customer or for the supplier, sorry. And we need to also put the interwinding capacitance here, okay? So if we take the interwinding capacitance, place it here, and we run again the simulation, okay, now it's faster. And what we will see in the switching node, it's something, okay, more reasonable, okay? We have a huge ringing, but the voltage spike are not like in the previous waveform, okay? But here there is still a missing component that I talked before, okay? And we don't typically account it in the circuit, which is the parallel resistor, okay? And this is a very difficult parameter to model in the system because it's difficult to measure. It depends on the VH loop of the material, and it can vary regarding the frequency, regarding the temperature. So my recommendation is don't waste your time trying to get an exactly value. Just measure the voltage spike that you have. If you don't have any clamping, you will have the voltage spike in your system. So measure this voltage spike and the behavior, and then here adjust the value until you get the same effect that you have in the real hardware, okay? The only thing that you can know is that this parallel resistor typically is in the range of kilo ohms, okay? So you can, for example, try 1 kilo ohm, okay? And what you will see, it's a damping, okay, in the signal. And this is something like probably you find more familiar, okay? You still have oscillation, okay? But then you have the waveform, okay. So as you can see, it's very important to account every parasitic, okay? Because you can also add here the intra-winding capacitance and the capacitance for the diode that is affect to this part, okay? But here, typically, in most of the case, the COSS for the MOSFET is the ones that dominate this oscillation and also the leakage inductance of the transformer. So if you cannot reduce the leakage inductance, because in the previous design, we have interleaving and it's very small leakage inductance, the only way to fix it is adding a snubber, okay? And the good part here in the LT-SPICE that you can check different values and adjust until you can do, of course, the calculations for the snubber, but before test it in the real hardware, you can place here the value and see the effects of in the real circuit, okay? And here you can check also the power loss in the, for example, in the resistor, on the current in the capacitor, okay? In case that there is a problem here, okay? And yeah, so here the conclusion for this part is don't care only about the leakage inductance, also place the correct capacitance is the system, and don't forget about the parallel resistance, because as you can see, it has a huge impact in the hardware, okay? And that's all, okay? So before going to the Q&A, Ellie, if you want to comment this. You are mute, Ellie.
Thank you, Marcos. Yeah, I wanted to explain very quickly something about the offer we have this week. For those of you that want to try Frenetic AI and Frenetic Magnetic Simulator together to experience the whole workflow and to try in your own use cases, this week we have this offer. You can use unlimited Frenetic AI and Frenetic Magnetic Simulator. We wanted to include the basic support, so we think this is important, and it's going to be also include monthly live technical webinars and special sessions only for clients. So this is the pricing. Important to take into account that this special price is for a minimum of 1 year contract. So you can think, and if you want to explore for free first the both tools, you can use the link I have shared in the chat for everybody. And that's all. If you go to the next slide, Marcos, I only want to, after the Q&A part, our next live webinar is going to be with Marcos again next Wednesday. And the title will be how a top tier client redesigned the inductor in 72 hours. So you will receive the recording and the invitation for this webinar. And now, Marcos, I think we have some questions about your
yes,
or today.
Yes, and the three questions are related with the same topic, with this the auxiliary winding, okay? So I think that I can answer the three together. So first of all, let's go back to Frenetic, because one of the questions is if we can simulate what happens if we place the auxiliary winding here, okay? And we have the auxiliary winding and the primary with the secondary winding in a sandwich interleaving, okay? So when this is running, the next part, why it's important to place the auxiliary winding close to the primary side, okay? Maybe I not explained myself properly, okay? But here the thing or the key parameter to figure out is first of all the leakage inductance, okay? Which at the end it's a relations between the coupling between two windings, okay? So in this case, as we are looking to a good or a proper, okay, what we want to have, because the leakage inductance can affect to the output voltage, okay? So if we want a proper regulation for the system, we want to reduce this value as maximum as possible, okay? And if we have it referred to the primary, what we want is a good coupling with the primary side, okay? And another reason that I also found is that this kind of feedbacks, okay, are more affected by EMI. It's not like the autocoupler that has more, let's say, defense until these effects. But in the auxiliary winding, you can have some interference, okay, from the different parts of the system, and this auxiliary winding, if it's close to the secondary side, can induce to the secondary side negative effects that we don't want, okay? So these are the two main reasons to having the auxiliary winding if it's the auxiliary winding in the primary side, okay? So here, checking to this part, okay, if we place the auxiliary winding in the first layer, okay, well, we have it close it to the, okay, let me open it here. We have it close it to the primary, it is true, but it's not inside the two primary layers, okay? So here, yeah, it is true that the leakage inductance for the secondary side, it's better, but we are with having more leakage inductance here in the auxiliary winding, as we can see here, we have 125. Okay, more questions. There are some typical core shapes associated with the flyback transformers at the fourth core. Is there a reason why and what shapes are typically used? Okay, so there is no like a specific core shape for flyback transformer, but it is true, or it's right that there are more common shapes, okay? Because at the end of flyback converters has relative low power, okay? Comparing with topologies like phase full bridge, LLC, and these kind of things that are in the range of kilowatts. That's allow the designer to use shapes like, for example, the DFD. The DFD shape, maximum shape is EFD 30. So you cannot use this shape if you have 200 watts or 300 watts in the converter, okay? And also EP, and these kind of shapes are, let's say, an optimal way. Sometimes if we compare with the classic E-cores, okay, that it's not the best shape in terms of effective parameters, okay? And it is very common to see, for example, in 65 watts flybacks for laptop charger, the RM, okay? It's not like a standard, but most of the designs that you will see or reference design are based on RM shapes, okay? Which can offer a good isolation between the primary and the secondary just for the shape thing, okay? And the last question, how we can reach it by a toroid call, because at interleaving one is not possible. Well, with a toroid core, what you can do is to twist the windings, okay? What you need to be careful is about isolation. If you have the primary and the auxiliary, I'm not sure, okay, because to be honest, I don't check it, but probably you can twist it together. But you need to be careful about the isolation, as I commented. Maybe with the enamel is enough, and if not, maybe with some sleeve or something like that. Okay.
Marcos, I think we are running out of time. So
Okay.
thank you everybody for connecting today. I hope we see you next week in the next webinar. And thank you, Marcos, for the complete explanation of the flyback common mistakes.
Okay, thank you.
Thank you, bye-bye.
Bye.